Hi everyone. Today we're going to be completing our notes on 4.6 modeling exponential and logarithmic equations. I want to start off with this term, relative growth rate. We're going to denote this using the variable r. This represents the rate of population growth expressed as a proportion of the population at any time. So for example, if we have r equals 0.02, that at any given time t, the growth rate is 2% of the population at that time t. So note that we can denote the growth rate as 2% as a percentage, but we can also express this as a decimal, 0.02. And in fact, when we plug it into our equation and evaluate, we're going to be using this decimal representation. All right. So let's take a look at what this means. In summary, the population would grow larger and larger amounts. Okay, so this growth rate is just saying that it's growing by a larger and larger amount. Okay, so for example, if we wanted to express some population f, we would have an initial value I, our growth rate e, or rather our growth factor e, our growth rate, which is r, and then time to the power rt, which t is time. Okay, so this would represent exponential growth. If I wanted to show exponential decay, or a population that's decreasing, this would be represented as f equals our initial amount, e our decay rate, or decay factor, to the negative rt, where that r value, that rate, is negative, and this would denote decay, or in other words, a decrease in population. So let's take a look here. The population of a certain species of fish has a relative growth rate of 1.2% per year. It's estimated that the population in 2000 was 12 million. So now I want to estimate the fish population in the year 2005. So I know that this is growing at 1.2%. I can express this as a decimal, 0.012. The population, the initial value, was 12 million. So we can say that the population is equal to the initial value, 12 million, times e to the 0.012 times t. Well, I know that the time is 5 years later. We're talking 2005. So let's go ahead and evaluate this. Take out your calculator. Our answer is going to be in terms of million. Yes, you could plug in your initial value as 12 million, 12 with 6 zeros. I'm just going to express it as 12 and just know that our answer is going to be represented as in millions. Okay. Don't forget to use that e, that numerical constant e. That's going to be right here in the pi key. And we're going to raise that to the power 0.012 times 5. Control Enter is going to give us 12.742 million. So we can see that in 5 years, the population grows about 742,000. Number 2, a tea kettle is full of water, is brought to a boil in a room with temperature 20 degrees Celsius. After it's turned off, the degree to which the temperature of water declines can be modeled by the exponential function given below, where f is the temperature in Celsius and t is the time in minutes. What was the initial temperature of the water? All right, so if I'm looking at this here, that tells me that the initial temperature is um, that scalar multiple in the front. So that would be that 80 right there. So that tells me that the initial temperature was 80 degrees Celsius. Using the fact that temperature decreases to 75 degrees Celsius in 15 minutes, find C, the relative rate of decay. Round to 3 decimal places. Okay, so we know that in 15 minutes, the temperature is 75. So what we can do is say that the temperature is 75, where t is equal to 15. So this is equals 80 e to the c times 15. We're plugging in 15 for t, and then plus 20. Let's go ahead and solve this. So first thing we're going to do is subtract 20 from both sides. We get 55 equals 80 e to the 15c. We're going to divide both sides by 80. And so we get 55 eightieths, which I know both have a factor of 5. So this would be 11/16 is equal to e to the 15c. And then rewriting this as a log, we get the natural log of 11/16 is equal to 15c, where c is equal to 1/15, the natural log of 11/16. This would be the exact answer, but let's go ahead and find a decimal approximation. So I'm going to do control divide to get my 1/15. We're going to do our natural log of another control divide, 11/16. Control enter, and that gives us negative 0.0249, or 250. So negative 0.0250. All right. I guess if we're rounding to 3 decimal places, we would just have 0.025. All right. As a percentage, this would be negative 2.5%. Go ahead and flip the page. The graph to the right shows the population of a rare species of bird, where T represents the years since 1999 and N of T is measured in thousands. Find the relative growth rate of the bird population using the point provided on the graph, 3,200. Okay, so to find the relative growth rate, I know that we have our ending value of 3,200 is equal to the initial population, which I can see is right here at about 1,500. Okay, times e to the RT, where R is what we're solving for and T is 5. Okay. T is 5 because we're evaluating the function N of T. N of 5 is 3,200. All right, so let's go ahead and solve this, dividing both sides by 1,500. We get 3,200 over 1,500, which reduces, equals e to the 5r. Let's see, then we would take the natural log of both sides. So the natural log of 32/15 is equal to 5r. And then dividing both sides by 5, we get r is equal to 1/5, the natural log of 32/15. So that would be our exact answer. Let's go back to our calculator to get the decimal approximation. 1/5, the natural log of 32/15. Control enter. We get about 15%, so 0.152. Okay, so this population is growing at about 15% every year. So what is the bird population expected to be in 2020? Well, if 1 year is the year 2000, then 21 years would be 2020. Okay, so now we can use our exponential model using r in our equation. So N of T is equal to our initial value, 1,500, e to the 0.152 times 21. So T here is going to be 21 because 2020 is 21 years after 1999. All right, so now we can just go ahead and evaluate. What I'm going to do here is I'm just going to plug this into the calculator, and I'm going to show you a few tricks here. First things first, we could just take this as our answer. I'm actually going to store this. So in order to store this exact value as a variable in your calculator, you can hit Control and then var, or var for variable. Over it, it says STO, which is storing as a variable. I'm going to store this as the variable r, and when I hit enter, it's just going to repeat this value. And because this is the exact value, this expression right here, anytime that I recall the variable r, it's going to give me that exact value. This helps when we're making iterative calculations. So when we have a calculation and we're using it for another calculation, it's great to have those exact values versus rounded values, and that improves the accuracy of your final answer. All right, so let's go ahead and plug this in, where we have 1,500, 1,500 times E. So going back to that mathematical constant, e to the 21r. And so I'm using that variable r as my 15% here, the 0.15. Okay, I'm going to hit Control Enter, and that's going to give me a decimal approximation of about 36,152. Okay. Um, Notice that we do have a decimal place here, 0.46, but we are talking about bird populations in thousands. Okay, so know that we can't have a fraction of a bird, so we can't have 0.46 birds. So we're going to truncate this answer just down to 36,152. All right. We got one more for us today. Radioactive substances decay by spontaneously emitting radiation. The rate of decay is proportional to the mass of the substance. Half-life refers to the amount of time that it takes for a substance to get down to half of its original size or original mass. Seaborgium has a half-life of 1.94 minutes, or just under 2 minutes. A research team successfully synthesizes 1,500 atoms of this highly unstable element. Find the rate of decay R. Okay, so we know that it has a half-life of 1.94 minutes. Okay, so suppose that we have an initial value of 1,500. In 1.94 minutes, we would expect the amount of this element to be half that of 1,500, or in other words, 750. So that tells us that our output, the ending value, is 750. The initial value is 1,500. E to the R times 1.94, where T is measured in minutes. Okay, we're going to solve this. So dividing both sides by 1,500, we get half equals E to the 1.94 R. And so then the natural log of 1/2 is equal to 1.94 R, where R is equal to 1 over 1.94. Natural log of 1/2 is the exact answer, but let's go ahead and find a decimal approximation. So control divide, 1 over 1.94 times the natural log of 1/2. Control enter, and that tells us that our rate is negative 36% or so. Okay, so negative 0.357. Okay, write a model that would help you find the amount A of seaborgium left after T minutes. So this would be the amount is A equals the initial amount, 1,500, e to the negative 0.357, which is what we just found. That's that decay rate, times T minutes. Use your model to approximate the number of atoms remaining after 5 minutes. Okay, so because we're going to evaluate this, I need to use that rate again. In order to evaluate, this would be A equals 1,500, e to the negative 0.357 times 5. Okay, I'm going to go back to the calculator, and I want to keep this value, so I'm going to store it again. And I'm going to actually use that same variable r, and what that's going to do is it's going to overwrite the previous value for r. When I hit enter, that tells us that we've overwritten it. And if I wanted to recall it just to show you, we can see that it's that new value. All right, so let's go ahead and evaluate 1,500 times e to the power of r times 5. Control enter, and we get 251.33, or 328, we'll say. Okay, and those are atoms. Okay, again, because we're talking about whole atoms here, we're going to say that there are 251 remaining atoms. Okay. According to your model, how long will it take for there to be only one atom left? So that's going to be the output. We want just one atom, and that would be our output. So equals our initial 1,500 e to the negative 0.357, and then times t. So we want to solve for t here, and that's going to tell us how much time it's going to take to have one atom. Okay, dividing both sides by 1,500, we get 1 over 1,500 equals e to the negative 0.357t. And then taking the natural log of both sides, we get the natural log of 1,500 is equal to negative 0.357. t is equal to 1 over negative 0.357 natural log of 1/1500th. Okay, so let's plug that into our calculator. We have 1 over, we have r already, so I'm going to just go ahead and use my variable. Natural log of 1 over 1500. Control Enter. About 20 minutes or so, so 20.468. Okay. So this has been our notes on modeling exponential and logarithmic models. We're going to get a lot of practice, so we'll see you tomorrow. Goodbye, everyone.